Okay, let's solve this problem together. We can solve this problem in two ways. The first one is using DFS. However, before we move on, this format is not very easy to use, so we are going to somewhat change this format. Last class, we talked about adjacency list. So we are going to create adjacency list to represent this graph. So we have n number of edges, and we're going to store the adjacent vertices in this adjacency list. And for two nodes, what we're going to do is, to this adjacency list, we're going to update the 8th vertex as B as its neighbor, and B has A as its neighbor, because this graph is undirected. Okay, so this is the first step, converting this naive representation into somewhat more intuitive representation. In fact, this representation is more useful for implementing the rest of this function. And we're going to use stack here. We're going to initialize our stack with the source or the starting vertex. And we're going to make a visited set. And we're going to add the nodes we have visited to this visited set. However, as I told you, you can implement the visited as this list, like n that contains n false. And while this stack is not empty, we're going to first retrieve a node like this. And if this node is destination, then we're going to just return true. And if this node is in visited, then there's nothing we need to do more. So we're going to just pass this step. Otherwise, we are going to add this node to the visited set. And for neighbors of this node, adjacency list, and we're going to retrieve the neighbor of this node, the current node. And to the stack, we're going to append all neighbors like this. And after we process all the nodes, if we cannot reach the destination, then we're going to return false. So this is the first solution using DFS to solve this problem. Now, of course, there is another way of solving this problem using BFS. And we're going to do the same thing for BFS. We're going to make this adjacency list like this. And here, I would like to introduce one library. You can import collections. And these collections provide a QADT data structure called deck. So basically, you initialize this one with source. However, you can just use our list like this. And later on, we're going to just use top 0 like this. So they are basically the same. However, this one takes ON internally. However, these collections back provides O1 operation. So you better use Q from collections. Okay. And we're going to make visited as a set. And we're going to initialize this one with source. Oh, and while Q is not empty, what we're going to do is we're going to get one node from this Q, and pop 0, this one, becomes top left in the case of deck. And everything else is pretty much the same. We're going to check whether the current node is destination or not. And for each neighbor, we need to inspect all neighbor in this adjacency list. We first need to check whether this neighbor is visited or not. If neighbor is not in visited, then we're going to add this neighbor to the visited set. And to the queue, we're going to append neighbor. And after we process all nodes, if you cannot reach the destination, we're going to return false. So basically, DFS and BFS look similar, but somewhat different. So if you just want to check whether there is a valid path or not, we can use both DFS and BFS. All right. By the way, I should have mentioned this before. However, thing is, DFS and BFS are one of the most frequent topics that appear in coding interviews or coding tests of tech companies. And if you could solve this problem or the next problem, then I guess you can enter some big companies like Samsung or LG, because they give this kind of problems every year. Anyway, so that was a short brief information. And the second problem we're going to solve today is this one. I'll show you the picture. Okay, so this is our second problem. There was one question. What is the time complexity of DFS and BFS? Basically, we need to visit all the nodes. It's going to take ON to visit all the nodes. All right. So we don't usually think about the time complexity of BFS or DFS because we basically try to visit all the nodes. All right. And the second problem we are going to solve is this one. So we are going to get some grids that looks like this, 0, 1, 1, 0, that looks like this. And our purpose is starting from the left top, we want to go to bottom right. Okay. So from this position, we want to go to the bottom right, top left to the bottom right. And we can go in the diagonal direction. And to reach the destination from source, we need to pass two grids, this one and this one. And that is going to be the output of our function. I'll give you a second example. And in this case, we're going to receive this grid 0, 0, 0, 1, 1, 0, 1, 1, 0, like this. And from the top left position, we start here. And the only grids we can go is 0. So we cannot go in this direction or in this direction. We cannot go here and here. So we need to take the right direction at the first. And here we can go to this position because we can move diagonally. And then we can go down and can reach the destination. And to reach the destination, we need to pass 1, 2, 3, 4 edges, a node. So the answer is going to be 4. And in this case, if the first node is 1 here, then we cannot start from this node. That means we cannot reach the destination, and the answer is going to be -1. Okay, so our second PPP problem is given grid. We want to start from the top left and want to reach the bottom right. And the thing is, in this case, you cannot use either DFS or BFS. However, you just need to use one of them. So first, determine which one to use to solve this problem, DFS or BFS. And then try to implement this function.